tradition, if possible. It seems like it's been talked down a lot at this meeting so far. I know that everyone's tired, but the worst thing is that the speaker is very tired. So I will try to go less time than what's given to me. I would like to express my thanks to Francesco and Samuel. I think you had something to do with organizing this meeting, for organization of this meeting. And Francesco, I wanted to express my gratitude to you, Francesco, for inviting me to this meeting. It's been a real experience seeing the intensity of this kind of meeting. It doesn't happen that intense in the United States usually. There's been a lot said in the last few. Well, I've seen a lot of really interesting talks in mechanics, by the way, in the last 3 days. And that's the experience that I've had. Now, in the last few days, there's been a lot of talk said about the principle of virtual power. And I'm not going to use that principle in this talk at all. But I want to describe a generalized continuum mechanics theory using the classical laws of continuum mechanics, the balance of mass, linear and angular momentum. Now I have to remember how to do this, so the setting of my talk, I think I better, the setting of my talk is basically, I conceive of this body. The picture is an arbitrary part of the body. So the body, I've not drawn the body. This is an arbitrary part. And I put a corner on that arbitrary part, C. This is the arbitrary part of a body at time t in its motion. And so I want to discuss in this lecture 2 types of contact interactions that can take place. One is the classical surface contact interaction, T, as you see, taking place at a point whose unit normal on the oriented surface of the part is N. And the other contact, and that is due to the contact with the rest of the body. And the other contact interaction, which I will think exists, is a generalization of that, and many of you have done that, which is Q on the corner. And it is also an interaction with the adjacent material of the body. And both of these are intensities or specific forces. T is per unit area, and Q is per unit length. And of course there's body force that acts. In addition to that, I'm going to allow the possibility of couples. And you see that in M. And you see that the corner is distinguished by a normal to the surface, N plus and N minus, where the corner comes together. And the corner may end, as it's said there. There may be many corners, and I'm just drawing one. So the corner is acted upon by the traction Q due to the contact with all the other adjacent material in B. The boundary surface is acted upon by an outer traction. And there's this volumetric interior which carries this body force. That's what I'm thinking of. Now, I'll introduce fundamental fields at the beginning of the talk. The fundamental fields, besides the motion of the body, which will not play a major role, I'm going to concentrate on the contact interactions. The fundamental fields that I will introduce, well, there's the mass density, rho, at the top, which I assume will be measured per unit volume. and conserved throughout. There's a surface traction, as I alluded to a moment ago, which is a measure of the force per unit area. And I will assume in this talk that contact interaction, surface traction, is a function of the normal and the second fundamental form, which describes the curvature tensor of the surface. One could take higher descriptors of the surface besides just the surface gradient, which is the fundamental form, but I will not do that here. It doesn't complicate it too much further to do that, however. The function, let's see, where am I here? I guess here. The function t is a function of n and the gradient, surface gradient of n, which is a symmetric tensor from differential geometry. And that function is defined for all n and symmetric tensors b, n unit vector, and b annihilates n. So if b acts on n, it's 0. So that's sort of like a two-dimensional tensor tangent. The surface couple, M, oh, and by the way, there's a T star there. By the way, this is a smooth surface that I have. This is not a potato. This is a potato pancake, if you like. This is a smooth surface out of the interior of the body that I've drawn here, S of T, a smooth surface. That is an element of the body, just like the potato is, but that is also an element of the body. And on that surface, the traction acts, and there's a T star that acts on the opposite side of that. And T star is independent of T. There's the action of the rest of the body on that side of the surface as far as force per unit area is concerned. There's an M, a surface couple, traction, and an M star, as you can see. The M is on the oriented surface with orientation N, and the M star is on the opposite side, unrelated at this moment. And it's just the action of the rest of the body. And on the edge of this smooth surface that's been taken out of the body is this third quantity called F, which is on the next page, unfortunately, but I've drawn another surface here, but F is an edge traction. And F is also due to the contact of this surface with the rest of the body. And that's a force per unit length of the edge, F. It does not need to lie in the tangent plane or any particular direction, have any particular direction. It's a function of the descriptors of that boundary of the surface, which is the curve, and the descriptors that describe that could be taken, and as I do, to be the normal to the surface at that point and the normal to the edge, which is in the tangent plane to the surface at that point. Those two geometric objects could be used to describe the curve. That function is defined for unit vectors nu and n, which are perpendicular to one another. So it's defined on a manifold. Now, on this figure, which I draw as a cornered surface, there are surfaces that are smooth. There are parts of this body. There are surfaces with corners that are parts of this body. And I draw this surface as having a corner, C. And on that corner, there is this additional corner traction, Q, that is supposed to exist. These are the fundamental fields that I'm taking out of the hat and putting on the table to base the theory on. And it is a function, as I draw it here, of the descriptors of that corner, which is n plus and n minus. Now, this is not important. I would not have to say anything about that Q except that it depends upon the corner. But I put something explicit here, and I'll come back to that later. N plus and N minus. Okay. So those 4 fields so far. The traction, one side of the other side. The couple traction, one side of the other side. The edge traction around the boundary of a smooth surface as well as a cornered surface around the outer boundary. And the edge traction are the 4 fundamental contact interactions that I will concentrate on. Of course, there's body force field that acts throughout the interior of a volumetric part of the body. Now, let me now bring up the fundamental balance laws, which I will use for developing what I have to say. So let's consider a smooth-oriented surface inside of the body. I will not, in this talk, allow that surface to have its own density. It could. It could have a mass density per unit area. But I will not, it has no inertia, in other words, in this talk. It's not important, but I'm leaving it out here. It has no inertia. So the balance of force is the balance of linear momentum, in that case, for the surface. And the balance of force for that surface is simply the integral of the sum of the tractions that are acting on each side over the area, plus this edge force around the outer boundary of it, summed up, 0. Now, you can prove something from that, something very important to the rest of this talk, which I didn't find easy to prove, and I was going to talk a little bit about it, but I won't in the late day, okay? Unless there's a question afterward. I'll come back to that, what you can prove. Here's the theorem that you can prove. You can represent that edge interaction force at any x inside of the body. There is a linear transformation. I call it J, which is a transformation of 3-dimension vector space, okay, into second-order tensors, if you like, or linear transformations. So it's a third-order tensor, if you like, J. It depends on x and t. It's independent of descriptors, of any descriptors of that surface. I will call it, out of tradition in the other literatures that I've read, the hyperstress tensor field. But that's just what other people might call that. Such that this is the representation for that edge force per unit length. You could say it is bilinear in n, the normal to the surface, and nu, the normal to the edge of the surface in the tangent plane. And I didn't find it easy to prove that. And I will come back to that if there's a question later on. So you'll just accept that. That's an important, major part of what I have to say in the rest of this talk, as some probably can guess. My proof does not depend upon Cauchy or tetragonal or these triangles, or because the plane, this is not a plane surface, it's a bent surface. My proof depends upon setting this statement about balance of force into a variational statement. And that's all I can say about it at the moment. Okay, so accepting that, I would like to go to, I want to go down a page. No, I don't want to go there. I want to go, well, I'll have to go this way, I guess. This way. And this is the proof, which I will come back to if there's a question about it. Okay. Accepting the fact that that edge force was represented in that bilinear way through the third-order tensor J, which exists, you can integrate that along the boundary of this smooth surface. And the edge integral will become packed inside of the surface integral in the force balance as the divergence, surface divergence of J n tangential. The tangential means is operating on tangent vectors to the surface, basically. So that is the new expression after the representation theorem of the balance of force. And from that, what you get is a jump condition that T star is equal to, or T star plus T is equal to minus the divergence, surface divergence of J n tangent. Now this should remind people of Laplace, the classical bubble dynamics and free surfaces on water. But across the surface there's surface tension sometimes, and this reminds you, be mindful of that kind of thing. But that's a jump condition, which I will use. So let us turn then to the balance of moments, or the balance of angular momentum. In the case, no inertia for the surface, balance of moments. Balance of moments is simply picking up the moment of the contact actions, as I see there, the T plus T star and the F with their moment arms. O is an origin you pick, if you wish, plus the moments of the coupled tractions on each side of the surface, M star, and that equals 0. Well, that doesn't give much interest to the story, but it does give a jump condition. If you were to use what was just derived for the T plus T star and the jump condition, as I just mentioned there, you can transform this balance of moments into the equation at the bottom of the slide now. And from that, you simply get a jump condition for M. So you can calculate M star on the opposite side if you know M on the one side. That's not going to play a big role. Okay, so now I turn to cornered surfaces. Cornered surfaces are also elements of the body. And they also have to be balanced. Linear and angular momentum. I will assume that that corner there is inertialess. It does not carry its own density, although it's not hard to include that in the story. So the corner does not have a mass per unit length connected to it, but it could. And in addition, the surface does not have a mass per unit length. So there's a balance of forces that has to hold. For the union of these two things, I guess, the surface and then the union of S in the corner as an entity. So there's the balance of force. Picks up all the forces that are acting on that surface and sets it equal to 0. But we know something about T plus T star. T plus T star is minus the surface divergence of J n tangent. You can replace the first integral by a divergence, which you can integrate. And you can integrate that first T plus T star around the smooth, on the smooth parts of this connected surface. So the boundary of those smooth parts is also the boundary of the outside of S, but also the C, the corner. And from that, if you would think of replacing that T plus T star with surface divergence, and then integrating, you'll see that some of the F is going to be all of the F is going to be canceled on the boundary that's outside of this surface. If there's any question, please stop me. And in fact, let me go to the next slide here for a moment. That's what the integral becomes. The F cancels. You simply have an integral over the corner equals 0. And it has to be true for all cornered surfaces in the body, so essentially for all corners that you want to think about. for all lines C. And of course, by localization, then Q must be equal to what's in the big parentheses on the J, and the pluses and the minuses. And this is in fact where I would not have had to say that Q depended upon S n minus and n plus in the original setup of this story. Okay, so the theorem is that the corner traction has the representation as given in the box, which I write as J with two curly brackets, which is the sum of nu dyadic n on the plus and minus side. It's the sum. But that sum, from a geometric point of view, is a symmetric tensor. You can prove that easily. That sum is symmetric. And the curly brackets on J means like an inner product on the last two indices, if you like indices, for the J. Okay? That's what that means. So in other words, only the symmetric part of J is coming into play in this representation. J operating on any W that's skew is 0. Okay? So we'll keep this in mind. Okay. So that's the representation of Q. Now the balance of moments for this composite cornered surface doesn't give anything new. If you look at it, it doesn't provide anything new. But I needed to look at it. So now we go up a step and we think about an arbitrary material part now. A volumetric part. One that has an interior volume, an open interior volume, and a surface that contains a corner or corners, or might not contain any corners. It's arbitrary, and you can select, I want to have a corner there so I can get somewhere with this theory. We need to have now the balance of linear momentum for this composite structure. The P, union with its boundary, and the corner. And so you can see that that is the statement of the force equal to the rate of change of the linear momentum. And of course you can take the time derivative inside on the right-hand side and put a material time derivative on the V, if you wish, because mass is balanced. So you can do that. Moreover, you know something about Q. I just showed that there was a theorem that Q has a representation in terms of J, this hyperstress, third order tensor, and the curly brackets of the descriptors of the corner. If you use the balance of mass and that, you will find that you can rewrite the top line by the bottom line. I have used the fact that Q is represented by the descriptors through J, and I have integrated by using the surface divergence theorem, because it's integrated over the boundary C of T in the middle equation, and you can put it as an integral over the whole boundary of the part through the surface divergence of J and tangent. And then I've already put the V dot. I've used the balance of mass in order to get that dot, that material time derivative on V. So that's the statement, and it has to be true for all parts. To be suggestive, I put this boundary of PT interior there. It is the limit of the interior volume to the boundary. The interior volume is an open set. The surface part P of T union C of T is the rest of the body. So to be suggestive, I've integrated over the boundary of the interior. And to be suggestive, I've replaced that P of T with PT interior. It makes no difference, basically, except for some mathematical curiosities in certain spaces. And if you look at that, you see it's an integral over a volume of something that depends upon, through t, it depends upon n, the second fundamental form of n through t. It has that divergence of s. But that area integral over the boundary of p of t interior is just a function, after all, of x and t. Time, x and time. And in fact, the right-hand side is a volume integral. So you have a relationship, a surface integral is equal to a volume integral, just as you would in classical continuum mechanics, or in much of physics, as a matter of fact, when it comes to balances. And one can prove something important about that. You can prove that this minus t star, which I've used now the jump condition, function of n, surface gradient of n, is a linear function of n. It does not depend upon the surface gradient. You can prove that. Now you can't prove that with Cauchy in this setup. But Epifanio and Verga and I wrote a paper in 1989 where we effectively proved that theorem, okay? Considering balance laws. Very important. T star was assumed to depend originally on n and the surface gradient of n. If you assume that it depend upon higher surface gradients, they would all go away with this theorem. The same idea would apply. I didn't want to do that here, though. It's independent, T star is independent of the surface gradient and depends linearly on n through a tensor H, which you could call the polarization tensor field if you go back to Tupin or someone like that. Moreover, if you put that back into the balance equation in the middle of the page and localize, integrate divergence theorem and localize, you get a balance law. Divergence of H plus rho b is equal to rho v dot throughout the interior of the body. Okay? So you get a lot out of that. All of that is coming from the first representation theorem for the edge force. Now that H tensor has no particular symmetry properties to it at all. It's a second order tensor. It has nothing, but I'll come to that in a little bit. And I'm referencing the paper with Verga in the Archive for Rational Mechanics and Analysis of 1989 for the proof of that theorem that I just stated. A major conclusion at this point is that T, I had T star before, but T star and T are related by this surface divergence of J n tangent. T itself, which is a function of n and the gradient, surface gradient of n, can be written as Hn from the last theorem minus the surface divergence of Jn tangent. And if you use the decomposition of the second order tensor Jn, J is third order, operating on n as a second order tensor, if you decompose that into a tangent piece and what's left over, and substitute that into the equation right above it, you'll find that T depends upon n and the surface gradient of n in that specific way. There's a part that's linear, the first two terms in n. There are parts that contain gradients of n and surface gradients of n and surface divergence of n, which is related to the mean curvature. But that's an explicit formula. You might call that a generalization of the Cauchy theorem, because Cauchy's theorem in classical continuum mechanics would only give you a linear dependence on n. And as a matter of fact, if I go back clear to the first slides that I mentioned, where I said I'm going to consider a smooth surface with edge forces on it. If You say, well, I'm not going to allow edge forces on that surface, because in classical continuum mechanics, they are not allowed if you're just doing classical continuum mechanics. If you do that, then T becomes Hn. The J is 0 everywhere. Okay, so now we go to the balance of angular momentum then. See what can come out of that. An expression of the balance of angular momentum is at the top two lines. The top two lines are expressing the moment of the T, the moment of M itself, the couple stress, couple traction, the moment of the body force, the moment of the corner traction, and the moment of momentum, rate of change. Now, if you replace H, which came into play a moment ago, with T by the boxed equation, I'm just defining a new symbol, T. Replace the H with the T by that equation in the box. Some people call that stress tensor field, but it doesn't. You can call it whatever you wish. Just make the replacement. Then the balance of angular momentum at the top two lines becomes exactly the last equation on this page. The integral of the axial part of T minus T transpose. Now, the axial part of a skew tensor is a vector. And for those, many of you know what an axial vector is and how it's related to the skew tensor. If there's a question, I'll come back to that. So that has plus the integral over the boundary of M, after you do the substitution and do a bit of work, M minus N cross Jn operating on N. Jn, second order tensor, operating on N, it's a vector then. Must be 0. Now you recognize there that you have a volume integral and a surface integral that have to add up for all volumes, for all choices of PT. And so again, you can use localization argument. Here you could use actually Cauchy to show the Cauchy tetragon argument, to show that couple stress, to show that there exists a couple stress tensor M, such that on the area integral, small m, the integrand of the area integral is equal to capital M operating on N. All right? It has to exist in M to do that. Of course, I'm assuming all kinds of smoothnesses in this talk. So you get the boxed equation that the moment, or the couple traction, I called it, M. I assumed that it was a function of N in the beginning. That was the descriptor of the surface orientation. Depends upon N linearly through this couple stress tensor M that comes into existence now, and then cubic on N through the first term, N cross J N N. Okay? So we have a representation now for the couple stress tensor. In addition to that, if you put that back into the integral equation, you find that the axial part of T minus T transpose plus the divergence of M must be 0. If you want to take capital M to be 0, then T is symmetric. That's what that would say. You don't have to do that, but that's what that would say. And you can note that if you replace the H with the T by the top equation in the box, that the balance of the dynamical equation for this theory becomes the divergence of T minus the divergence of J, a common combination that you see, plus rho B is equal to rho V dot. Okay? Moreover, if you replace, and in addition, not moreover, but if you replace the T with the H by the top equation into the earlier representation for the traction, you just see that it's equal to Tn with minus 2 times that divergence of Jn, plus other terms that are nonlinear in N, and gradient of N, surface gradient, and gradient of N. That that's the representation which I would say is the generalization of the Cauchy of Cauchy's stress theorem. And when J is 0, this is then Cauchy's stress theorem. Okay. May be proven differently. So finally, let me comment then. So we have then developed equations for this generalized continua, which are commonly accepted by other means, using only the hypothesis on forces and force densities, force actions on the body, without, and so far proven the existence of hyperstress tensor and the stress tensor, if you call it T stress tensor, proven them. Whereas in the power, in the principle of virtual power, J and T are assumed up front. They are in the internal power that is laid down in that theory. Okay, so going to the power theorem, there are many power types that enter into this subject. One is the common T inner product V through the boundary of this arbitrary part, smooth part of the boundary. There is a rho B inner product V, which is the volumetric power coming from outside of the body. 5 minutes. And then there is a specific, I call it a specific hypertraction power. There's two types, with moment and without moment. With moment, it's just M inner product omega. Omega is the axial vector of the vorticity tensor. Axial vector of the skew tensor, skew rad V. That's the vorticity tensor. So it's not the vorticity vector. I think it's 1/2 the vorticity vector in fluid dynamics, but that's what omega is. And M dot omega is the hypertraction power with moment that's acting, coming into the body through the boundary. And you can re-express this M inner product W through the inner product of the associated skew tensors that come with those two axial vectors. The M is an axial vector, the omega is an axial vector. So that inner product is the same as a N cross J N N inner product the skew part of J N N dyadic N inner product with the gradient with the skew part of the gradient of V, but you might as well put the gradient of V there because it's an inner product with a skew tensor already. It picks up only the skew part. Okay, plus M N inner product omega. Okay, so that's the moment hypertraction power with moment, and without moment, it's just the symmetric part of J N dyadic N inner product. The symmetric part of the gradient of V, which you might as well say is the gradient of V, because the inner product of two, the one is symmetric, the other one has to be symmetric. Okay, so I just write grad V. So the total that's coming in through the boundary is simply the bottom equation there, and you use that now to construct the total power that is being supplied to this part. There's the T part, the traction part. There's this hypertraction part, both with and without moment. There's the MN inner product omega. There's the edge force, Q inner product V. There's the body force, B inner product V, integrated. That's the power coming in. Oftentimes that's assumed up front in the principle of power, virtual power. And there, then, the V is a virtual field. This is the V of the body. Well, now there's a theorem that can be proved, of course. You can prove a power theorem that says that the power in that is supplied to P can be split into pieces. One piece is the sum of the stress power, the hyperstress power, the couple stress power, and the time rate of change of the kinetic energy, and that's a theorem. So there it is. Pn is equal to what I've written there. Okay? I don't know how to get that off of there, but there. Well, the first term is the symmetric part of T. The symmetric part of T shows up now in this. It comes into in the proof of the theorem. Symmetric part of T, inner product with the gradient of V, or you could say the symmetric part of the gradient of V, or the stretching tensor in continuum mechanics, which is called the stretching tensor. Then there is this J, inner product grad V. Just comes out of using divergence theorems and improving this and proving this theorem. There's the M grad, the vorticity or comes in. And then there's 1/2, the rate of change of 1/2 rho V squared integrated, which is the kinetic energy. So that's the rate of change of the kinetic energy. And again, I stress that the symmetric part of T is what enters this power theorem automatically. Now, if J was equal to 0, as it is in a classical continuum environment, right in the beginning, the first representation theorem would, you see, you just get the classical power theorem of continuum mechanics, with the exception of the couple stress term M that's there. I could have made body couples in this story as well, but I didn't want to complicate the issue, so there were only surface couples that were coming into this problem. So that's the story that I wanted to present. I wanted to make sure that I did not start with the principle of virtual power, but I ended with the statement of the power theorem. And I want to try to make absolutely clear that the proof of some of these theorems cannot be, I don't know how to do it anyway, with tetragons like the Cauchy theorem uses. I am keyed into doing variational work, and I prove these theorems using a variational argument, which is not difficult. For me, it's difficult, but to a mathematician, it's not difficult. So what I've done then is simply introduced appropriate contact interaction for the subparts of a body. The subparts are the open interior volume, the surface union, the corners. So I've introduced these appropriate contact interactions. I've applied the fundamental balance laws of continuum mechanics and arrived at field equations for a non-classical, you could call it second grade, but it doesn't need to be called that, continuum mechanics theory. And I've not invoked this principle of virtual power, but rather showed the existence of the stress and the hyperstress fields. Now, and these are usually assumed in the principle of virtual power. Now, last night, when I started thinking about my talk, seriously, I thought before, but seriously, after 3 days here, I thought there could be some controversies because of what I'm trying to say, and it's different from what has been said. So I had 2 Fernets before bed, 2 Fernets, and 2 Fernet, and I anticipate now a vino cantucci later. Does that make any sense to the Italians? Well, I learned that in Tuscany.
Knowing that we are talking about food, one can understand.
Well, I saw 2 old men one day sitting at a table in Tuscany having a great argument. And at the end of the argument, they brought wine and biscotti here, but right? And I asked my friend, what is going on? He says, it's vino cantucci. After the argument, you always settle the argument this way. So I'm looking forward to that. I hope I didn't go too far over. Thank you. Here comes the controversy now, I think.
In the last day, they mentioned the difference point between fractures and the about edge force. And I would like to illustrate the position of Roger. In my opinion, what Jason is doing is complete nonsense. And I promised to prove this. And I will not succeed. I pay a dinner to him and but I will succeed if you pay attention to me. This is the agreement. Okay. So,
Yes, now it's my turn.
looks like to have your view, but it is not true. It has a very different view. That is, what you are saying, if is that in the second order condition, even if you don't wish, a concentrated force appears to the core. Okay. Roger applies the force to the corners and goes follows this assumption and draws all the equations. The only thing I have to check before saying that you are completely right is to see whether the virtual displacements of the second order continuum can support the forces of this regularity. But another comment that I can make to you is that if everything works, you don't need, you need not put the force on the core. You can, if the continuum support an edge force, then it supports a line force along any point of the boundary, and it supports a surface volume force. Just because the regularity is one step back. So you should complete your view, supposing that this extra force that you have at the edge may be at any regular point of the body, and I am sure that your equations work as well. And the same for body forces which have a singular surface measure.
Let me just say that there is where that force came into play. In the balance of force for the union of S, its boundary, and the corner. That's where it came into play. If one sets Q equal to 0 there's a catastrophe that happens. CT is the corner line in the figure. It's the corner. C is the corner. If you set Q equals 0, there's a catastrophe that happens. Well, this is a force that is applied by the rest of the body due to contact.
I'm not saying that what you said. I am saying that the Q need not be applied to an edge. It can be applied to any line, even
on the smooth part.
Plus is the other one. This is balanced, and this so it is not comment. But I need to support Q. You don't need an edge. You can apply it at any line inside the surface.
Well, yeah, you could. I have to think about that because at smooth places, I conceive the contact action as area-oriented, as area-based, and because there is no line to pick out, so to speak. That's you say, well, you don't need a picked out line.
What happens in one dimension? Okay, you have a rope, and you can apply a concentrated load, but not a concentrated core. But you make a higher order continuum, which is the beam. You can apply the concentrated core, but you don't need not to apply it to an edge. You can apply it at any point.
Giampietro has always had an effect on me. Sometimes, quoting the Rolling Stones, he makes a grown man cry, but...
Roger, I just forgot, maybe you can remind us, the proof you have for the
first theorem,
Cauchy theorem or whatever, you skipped.
Yeah.
You make an assumption on, you did mention that it's an extremum, you're looking at it as you and Virga in that paper. What was the extremum?
Okay. The basic idea is if you have a balance law like that one, for example, for all S inside of the body, to all surfaces. Then you come up with a mapping, a one parameter field of mappings of that surface into, let's say, neighboring surfaces. It's a function of, it's a mapping of x's in the body to x's in space locally. So you first write down a mapping of that surface into a one parameter mapping. Okay, do you see that first of all? No, you don't see that, do you? Okay. You think of the points x that are carrying all those fields right now. Okay? And you say, I want y of x to be x plus epsilon u of x. Okay? Okay, so now I've changed x into y through a mapping. Now I have a whole sequence of family of surfaces. If that statement is true for one surface, it's true for the whole family, for every epsilon in that family, because they're all inside of the body. So if you take the variation now with respect to the epsilon, it's got to be 0, because that sequence is not changing. It's always 0. The sequence is always 0. So the first variation with respect to epsilon, take the derivative of epsilon, set epsilon equal to 0. That's the first variation. Okay.
Let's talk about this.
Yeah.
Third question.
The question and a comment. So the question is, here, I understand what is T and T star.
Yeah.
When S is the boundary of the body, then the meaning of T and T star is not quite clear. So I have...
Oh no, it is. Yeah, it isn't. It isn't on the boundary. This is only on a surface. This is just surfacial. This is a surface.
You use that on the boundary of the body.
Okay.
If I understand...
No, I did not. I did not use that.
The traction on the open body and on the...
I used T. I didn't use T star. T star is there on the other side of the body, but there's an open. There's the open volume, open set in the volume that has a limit, and it balances with that T star. Do you follow what you don't?
If you reverse the role of the interior and exterior of the domain, what's happened to T star?
There's the situation right here, right there. There's the situation. Now there is a T star, acts on the other side of that surface, but on the limit of the surface from the interior, it's canceled with that. It's canceled with that. All right?
From the external point of view?
Yeah. So I'm just calculating all the effect that the rest of the body has on that part. That's all I'm...
Probably it is simpler to say this way. The
surface, right.
So he acts on the oriented surface,
Yeah.
and the star acts on the same surface with
Opposite side. Opposite side.
Question number 4 here.
I wanted to ask exactly. Anyway,
Question number 5.
as everybody else in the slides, if you like, or
Pardon? You want the slides?
gathering all
Oh, you want some slides? Okay.
we're gathering all the
How do I...
let me know when you publish this book.
Okay, what's...
Just ask why do you consider that force F along the...
Just a second. Drop the arrow. Just he wants to ask a question here. Just a second. What?
I mean force F
Yeah.
not appear on the slide.
Because there is no edge to the surface.
Yes.
There's a corner, but the surface is a cornered surface, so there is no edge.
Why
Right?
do you consider that F depends on and
Yeah. That's the... I don't know how to go back here, but...
it's clear for me why you consider the dependence on that plus and minus for the corners. But why do you consider that? Yes.
There.
No. Okay.
Right there.
Yes.
And F was... and let me just go one slide ahead here. There's F again, and there it is, what you're talking about. Yeah.
Since we're also consider that depends on plus and minus. Why depends on
Oh, because F is the action of the rest of the body on the edge. The rest of the body on the edge. There's no rest of the body on the in the surface. The surface, there's no part of the body in the surface, right? It's the outside of the surface, which is in the body, that's acting on that point, and that's what F is. And I simply took the nu and the n to be surface edge descriptors. They describe the edge. I mean, if you give me an n and a nu field in space, I can draw a curve, that has that n and nu. If you tell me what I'm supposed to do, I can draw it and get an edge. So that's how I did it.
And that's it.
you have the corner n.
Yeah.
Do you have also to introduce
You could very well introduce points, and this is what's said in the abstract of the talk. Actually, you could conical points inside of the body points, or points at the end of the. Yeah, of course. And I decided to only talk about edge forces. The densities are per unit length. At the end, it would be forces. It would be forces. Possibly.
Fantastic.